All right, let's start. Do you have any questions? Okay, so we were discussing, right? So we were along the topics of basic, right? Continuous random variables. All right, and so here the word basic in quote because there are many basic models, right? And what's basic, uh, what counts as basic depends on which area of application you go into. But the ones we cover will be basic in the sense that you should see them no matter where you go, right? And the ones we mentioned were the uniform, right? Which we'll not going to repeat. The second one is the exponential lambda. The third one, right, is the normal mu sigma squared. Okay. So, you know what? Well, let's just. So for the exponential lambda, what should you remember about them, right? So the first thing is that the density is lambda e to minus lambda x, with the support being, could be zero, right? Because it doesn't count really. I mean, it's just 1 point. Probability, the support, right, is non-negative. So the CDF will be 1 minus e to minus lambda x, right? I mean, well, okay, sorry. Yes, right, because basically here it will be 0 if x is negative. And then the expectation is 1 over lambda. The variance is 1 over lambda squared, okay? The exponential models waiting time, right? Until an event, until the arrival, right, of an event. So, and of course, it's kind of custom made or custom built. You could just do it separately. You say, I want to model like the time to failure of, let's say, my laptop, right, as an exponential lambda. So this is also survival time, right? Because a lot of times the event that you're looking at is like the failure of something, but it could also be, right, the arrival of customers at a store. So it's connected to the Poisson, right, arrival. Poisson model, right? So in fact, we mentioned last time that if you have Poisson lambda as the number of events, right, within a time window, then the inter-arrival times, the time between events, right, are exponentials lambda. You just should remember that if you use exponential as the model for your time, then two things. The first thing is that, right, there's no upper bound on how long you have to wait, right? But I mean, as I mentioned, the probability that you wait more than, let's say, 10 units of time, whatever that is, should be pretty small, right? Because exponential decays very quickly. Or you can look at this, right? This is basically probability x less than equal to little x. And unless you have a very small lambda here, right? This will tend to 1 very quickly. The second thing you should remember, right, is that it has a memoryless property, right? Which basically says that probability x bigger than t plus h condition probability x bigger than t is probability x bigger than h. All right. I mean, it could also be expressed as this t minus s. So here you require, right, t h to be positive. Here you require t to be bigger than s. So again, right, why memoryless? The reason, again, is to think of x as the survival time of something or the waiting time of something, right? So you have your laptop having survived a year, right? And you asked, well, what's the probability it's going to survive the next 3 months? Answer, well, it's as if you bought a new laptop and has asked a question of what's the survival, right? After what's its survival chance for more than 3 months? Now again, right, a lot of us will feel strange about that conclusion, meaning that you would expect that, who knows, right? I mean, at least I would expect that my old laptop, right, is more likely to fail than a new laptop, right? The chance of it surviving the next 3 months is smaller. But if you think of it that way, there's nothing wrong with that. But what that means is if that's really what you want to capture, then exponential is not the model that you should use. Okay? If you use the exponential model, then you're committed to the memoryless property. Okay? So again, there's nothing right or wrong about a model. It's about whether or not it fits whatever phenomenon you try to describe. But the exponential is very popularly used, right, to model as a basic model for queuing time, right? In queuing model, queuing system, that kind of thing. So probably because it's easy to work with. All right. We'll talk a little bit today about what you can do if you want the rate to change, right? If you want the the memoryless property not to hold, and you still want something like the exponential model. But let's talk about the normal random variable. X is normal mu sigma squared. Then the PDF, right, is 1 over square root of 2 pi sigma squared eta minus x minus mu squared over 2 sigma squared. This one has support, over the entire real line. Okay. The CDF is not known, I mean, as a formula, but there's several notations for it. And I will go with the textbook, right, notation. All right, I mean, not that these two are wrong or anything like that. Symbol, right? There are many ways to express the same thing, but let's agree that we'll use this if only because it agrees with the textbook's choice, right? Okay. And we'll explain why this one is going to be the relevant thing that we. Oh, sorry. You know what? Apologize. No. This one is reserved for the standard normal. Sorry. So the only thing I want to say here is does not have an explicit formula. All right. And the one that we invoke a lot of time is the standard normal, okay? And the standard normal, of course, has the PDF square root 2 pi e to the minus x squared over 2, right? And this one, the CDF, right? Let's say this is denoted as this, and this is our choice. Okay? All right. And the normal, right, has the property that any linear transformation of a normal is a normal. Okay, I'm referring to this x here. Therefore, you have the Z transformation, right? Where you pull a normal back to its standard normal. X minus mu over sigma, right? Has standard normal distribution. Sorry, let me change my seat a little bit. I'll be right back. So what should we remember about the normal? So by itself, the normal is not really a model of anything. It is used as a model for error, okay? Like it's the normal is usually referred to, I mean, a sequence of IID normals is usually referred to as white noise, but that's in the context of linear regression or like Brownian motion and things like that. As far as we're concerned, the normal, let's just say for now that it's not really a model of anything. Let's just say like that. I mean, it's a model of white noise or error, but let's put that aside. But what we're concerned with is really, right, that the normal, while not being a model of something concrete, is the limiting, right, distribution of the sum of IID random variables, okay? That's kind of the message here, that the central limit theorem, which we'll cover, right, later on, says that if you have a IID sequence, right, IID means independent and identically distributed. Then if you take the sum, right, xi minus mu, all right, and you will sum from 1 to n, right, and you scale these guys by square root of n sigma squared, then this will asymptotically approximately have a standard normal distribution. Okay. So this is central limit theorem proper, which we'll talk about, later on. The reason I want to mention this is because what you are kind of asked to know in this section in normal random variables is the normal approximation to the binomial, which, as I mentioned, right, is a particular case of that, of the central limit theorem. Normal approximation, right, of binomial NP. Which says that, right, that the probability of, let's say X has binomial NP distribution. Then the probability, let's say, of A less than X less than B. Let me see if I need to do something here. You know what? Let me just not even do that. Let me just say that X, right, is approximately, all right, a normal random variable with mean NP and variance NP1 minus P when N is large. Or you will see something like this: X minus NP over square root of NP1 minus P is approximately a standard normal. All right. Now, you see that these two statements are one and the same thing. Whichever one you want to use, it's up to you. The reason why people don't like to use this expression a lot, even though it's correct, is because when N is large and you think of N going to infinity, then this is really infinity, that's infinity, and they feel uncomfortable writing it down. But in reality, right, N large here is like a finite number, like 30 or so. So, this makes sense, right? And you don't have to memorize the normalization form. You can keep two of them separate, right? NP is the mean of the binomial. This is the variance of the binomial. So also, right, the Z transformation will exactly correspond to that. So you don't have to memorize one more thing. That's all I'm trying to say. So what else do I want to tell you here? Be careful, right? That there is another approximation of the binomial, which is the Poisson approximation, right? That we talked about in the discrete random variable case. The Poisson approximation works when P is really small, right? P is close to 0. This, so in principle, should work for P not close to 0. This is not for a rare event. For a rare event, you should use the Poisson approximation. But for P around 0.3, 0.5, and then large, that's when you use normal approximation. So that's a sort of like the, I don't want to call it tricky thing, but if you have P small, like really small, like 0.01, then be careful. It should be about Poisson approximation rather than, right, for the binomial rather than normal approximation. Now, having said this, right, there is something called the continuity correction. Is it continuity correction? When doing normal approximation of binomial, like this. So the whole thing, right? Well, so not the whole thing. One thing that's pretty, let's say, beautiful, if you want, about a central limit theorem is that it doesn't state whether the random variables, right, that converge to a normal are discrete or continuous or, a mixed. In fact, right, the theory is true, whichever. Sorry, I missed one thing, right? This is with mean mu. As long as they have some mean, some variance, and their IID. I mean, there's some weaker version, but we're not concerned with that here. So you should kind of contemplate here a little bit about the meaning of the statement, let's say when these guys are discrete, because discrete means discrete numbers. What does it mean to converge to a continuous random variable? Well, the answer, of course, is it converges in distribution, meaning that the probability that these guys are in some range of values will converge to the probability that this guy is in the same sense in the same range of value. Okay, so it's converging in distribution. But anyway, the reason why is because the discrete to continuity transfer, right, has some, let's say, tricky business about it. Let's just be clear about. Let's just be concrete about, for example, right? So let's say X is binomial NP, right? You say probability X equals to K, right? So which on one hand is N choose K, P to a K, right? 1 minus P to N minus K. But if you transfer this to a normal, let's say you do that, normal NP 1 minus P, I mean, approximately, right? It's not equal, equals to K. Then you're quite off because the answer here will be 0, right? Automatically, because it's a normal random variable. It's a continuous random variable. Okay. While this should be a number, I mean, however small that is, it's still a number. When n is large, right? When n is like 100, then the probability that the binomial take on any particular value is small, right? Because there are 50 scenarios or whatever. But either way, right? This is a non-zero number, and this has to be 0, right? By definition, continuous random variable. So for that kind of situation, what you do is you convert this, right, into probability that K minus 0.5 less than X less than K plus 0.5. All right. And that's called the continuity correction. The reason is because, right, when you subtract and add 1/2, it doesn't change anything with respect to the discrete value, right? I mean, it's equal to 1, and the next one is going to be K minus 1 and K plus 1, right? There's nothing in between. However, this gives you some room to calculate the probability when you move to the continuous random variable. Are we okay? And yeah, right. So from here, you can do the Z transformation. Sorry, this is approximately, right? This is not equal. And now equal probability, right? K minus 1/2 subtract NP over square root of NP 1 minus P less than Z less than K plus 1/2 plus NP over square root of NP 1 minus P. Okay, so far. So, right, continuity correction, normal approximation, Z transformation. The last step here, which is pure formality, will be this. Meaning what? Meaning that any answer or any questions involving the normal distribution should be answered in terms of the CDF of the standard normal, or let's say must in this class. So having said that, I'll say immediately that I don't care about numerical answer, right, in this course. I mean, it used to be, right, that you guys will be asked to look up the normal table, right, at the end of the textbook. I think your textbook might still have the normal table at the back. But things are moving very fast these days, right? I don't think anyone look up any table anymore. The point being, right, is that you can access like a statistical software like R or Python, and you can look up, right? You can just call up, right? I think with Python, right? Uh, it's norm CDF. Might be in the SciPy package or the NumPy package. I forgot, but one of those packages, right? Of a number, then it'll give you this, right? So basically, what my point being is, right, that you don't need to look up any normal table. You should be aware of that as a historical fact, if you like. But people still store those information somewhere, meaning that if you want to translate, right, this into a numerical value, you can just call up the code on a computer. So symbolically, we should still express that fact, meaning that we should still express anything we need to calculate as something that the computer can answer. Do we understand? But that's that, right? We stop there. We don't move to numerical values because there's no need to. Any question?
Professor, in the step
Yeah.
where you're factoring for z for the right side, why are we doing plus NP instead of minus NP?
No reason because I just made a
Okay,
mistake.
thank you.
Thank you for that. Yeah,
On the
appreciate it.
bottom as well.
On the bottom, yes, I for some reason. Yep, appreciate it. Thank you. All right. Any other question? So let's take a look at some problems. Well, where are we? Okay. So this is question number 16, right? The annual rainfall is normal mu sigma squared, mu equals to 40, sigma equals to 4. What's the probability that starting this year, it will take more than 10 years before a year with rainfall of more than 50 inches? What assumption are you making? So how do we do this? So this one, right, is a geometric random variable, right, built within, or whatever, a normal, right, built within a geometric random variable, correct? So it's like the Poisson question, right, before. So there's a little p, right, which we defined as a probability that not the standard normal. The normal mu sigma squared is bigger than 50, right? And true to our convention, we need to do some statement to transform this into that, right? Where mu and sigma squared, mu and sigma are given like that. So that's called our little p. Then the answer will be more than 10 years, right? P. So notice more than 10 years could be 11, 12, 13, whatever. So it's really the probability of a geometric p, right, is bigger than 10. Meaning it's 1 minus, right? Anything that's less than 10, right? Up to 10. Okay, any question? Okay, let's continue. Next one is question number 23. Um, 1,000 independent rows of a fair dice. So two questions really. Approximate the probability that 6 will appear between 150 to 200 times. I guess the word is and here. Inclusively. Okay. So what would this be? So here you're dealing with binomial, right? With 1,000 trials, and you're looking at 6, actually any number, right? Because it's a fair dice. So it's 1/6. So you let X be binomial, right? 1,000, 1/6. Then what are you looking at? You're looking at the probability inclusive, right? 150 less than equal to x less than equal to 200. Right? And the first thing you should do is a continuity correction. Are we okay? And then, right, a normal approximation. So this is approximately. We can do this, where mu is 1,000 over 6, right? And sigma square is 1,000 over 6 times 5, 6. Okay? And then, of course, right, then we can move to a standard normal approximation. No, sorry, z-test standard normal, right? So 150 minus 1/2 minus mu over sigma less than z less than 200 plus 1/2 minus mu over sigma. Which finally, right, we write as the CDF of the standard normal. Any question?
Could you explain how you got the variance squared of 1,000 over 6 times 5 over 6?
Simple, right? It's the binomial. NP1 minus
Thank you. Yep, thank you.
So again, the trick is very easy, and it's usually this version that makes students not memorizing stuff, right? But if you look at closely, it's really individually each of them is mu. So you can also have sum of xi minus n times mu if you distribute the sum inside. And that's exactly the NP, right? And what is this? This is nothing but the variance of the sum, which is n sigma squared, because they're independent. And so in some way, this version, which is equivalent, is much easier to remember. But like I said, this is like an unorthodox way of writing it, because you are taking n to infinity. So people will frown upon this because this makes no sense as normal infinity. But as a application, is perfectly fine. Is actually even better, because like I said, you never really push n to infinity. In application, you pick a finite n like 30. So you could just plug that in. But again, right, it could also be frowned upon in application in the sense that your normal might have a huge mean and huge variance. But what I'm saying is, like, this is actually correct conceptually. But then if you take this as a middle step and then you can do the Z transformation, it's easier on your mind to remember rather than, do one swoop and then kind of transform. Any question? All right. So part B says if 6 appears exactly 200 times, find the probability. And I think this is also meant to be an approximation. find the probability that 5 will appear less than 150 times. That's just a question. How do we do this? So the first thing to remember, right, that the word if means what? Conditioning. This is a conditional probability. Okay. So what in the world does it have to do with, say, binomial approximation, normal approximation of binomial? Because you can guess that that's a theme here, right? The problem is not moving beyond that. But what does it have to do with, and where's the binomial? What binomial are we looking at? Well, the answer is as followed, okay? A direct observation, or not direct observation, direct intuition will tell you that condition on 6 appearing 200 times, then the distribution of 5, okay? So the number of 5s will be a binomial 800. With what kind of success probability? One-fifth. Why 1/5? Because in that 800, you know that 6 is not appearing at all. Does it make sense? So there's a group of 206 that we know are there. We just are concerned with the remaining 800, which we don't know what's going on. But one thing we do know is that none of them are 6s. So it's 1/5. All right. So we'll prove this statement rigorously, but that's the direct intuition. And then of course, right, the rest is just about something like 800 1/5 is less than, right? They say it's less than 150. So you do a continuity correction, blah, 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 like the above. So I won't do that part. I'll show you why this works. Any question? I mean, I'll show you rigorously why. I just explained the intuition. All right, so the rigorous calculation will work as follows. The probability, right? Let's say the number of 5 is equal to little k. Condition on the number of 6 is equal to 200, right? First of all, notice that by default, right, k here is going to be between 0 to 800, right? Because we toss a coin, sorry, we toss the dice to 1,000 times. But then this will be the probability, right? Number of 5 is equal to k, number of 6 is equal to 200. divided by probability of number of 6 is equal to 200. All right. Now the denominator is easy, right? It's the binomial. So it's 1,000. Choose 200. 1/6 to the 200. 5/6 to the 800, right? What about the top? The top is not something we discussed explicitly in the discrete random variable chapter, but it's kind of there. I mean, implicitly, right? It's called a multinomial distribution. Multinomial is a generalization of the binomial. So binomial, right? You only have one type that you're tracking, success, right? So basically think of the binomial as tracking two types, right? Type 1 and type 0. Type 1 is success, type 0 is failure, right? Among n trials. Each of them can be 0 or 1. But there's no reason why, right? There are only two types for each trial, two types of results. There can be 5 types of result, 10 types of result for each trial, right? And now what you're tracking is the number of trials of certain types. Again, think of the fair dice, right? If you roll a fair dice 1,000 times, what's the probability that, let's say, 5 shows up 100 times, 6 shows up 300 times, 4 shows up so many times, right? Things like that. Here we're only focusing on 5, 6, and not 5, 6. There's like a trinomial, if you will, right? So the answer is pretty simple. Out of 1,000, choose 200 for the 6, choose K for the 5, and then the remaining, which is 800 minus K. So that's a multinomial coefficient, right? That we talked about way back in the combinatorics chapter. And then 1/6 raised to the K, 1/6 raised to the 200, and then 4/6 raised to the 800 minus K. Any question? Okay. So the rest is simplification, right? These cancel. Yeah. So let's talk about, so these cancel for now, right? Let's talk about the simplification here. The multinomial coefficient, right, will be 1,000 factorial over 200 factorial, K factorial, right? 800 minus K factorial. And then the binomial coefficient is 1,000 factorial, 200 factorial over, and 800 factorial, right? So see, the final, the simplification will be 800 choose K. Right? So you have something like 800 choose K. And then, so the 5/6 to 800 here, I will write it as 5/6 to the K, and then 5/6 to the 800 minus K. You see, because when I mash this up, I'll have 4/5 to 800 minus K. And then I will have 1/5 to the K. And guess what? That's the binomial 800 1/5. that I'm talking about. Any question? All right. So now let's continue. So let's talk about 5.31b. So let's remind you of the context. The context is you're trying to write the whole problem really, trying to minimize over all values of a of expectation of x minus a, right? And in terms of interpretation, right? What you're doing is you are minimizing the L1 error, right, of the distance between the random variable x and a constant. You can tell a story here if you want, right? X represents the random location of some event. A is a fixed location of something like a service station. So you want to minimize, right, the distance. But as I told you, I think these days, right, machine learning is super popular. You should have seen something like a L2 minimization, right, which is linear regression versus L1 regression, right, which is called the lasso method, if I recall correctly, whatever. The point being is, right, L2 and L1 norm are very different things. But anyway, right, we're minimizing the distance in L1, right, of the random variable away from a number, right, a fixed number. And so for question A, x is given as a uniform, right, from 0 to some number. And don't confuse, right, these two things, they have nothing with each other. The choice, right, comes out to be the halfway, right? And I warn you that don't take this as universal truth in any way. It has a lot to do with the uniform distribution. And part B, right, kind of plays along with that because now they ask you to take an exponential lambda. Right, and do the same thing. So, well, what to do? Well, the first thing is, of course, to write down this expression, right? So expectation of x minus a will be the integral from 0 to a, right? If x is less than a, absolute value is a minus x, lambda e to minus lambda x. And if x is bigger than a, is x minus a, right? That's the expectation. The second thing is to do calculus with this by differentiate with respect to a and set equal to 0, right? How do we deal with that step? Then we integrate this and then differentiate with respect to a. Well, the answer is you can, right? That's probably what you would do, and that's legit. It's a calculus step, but it's still a little bit painful, right? Because there's an integration by parts and the numbers are not that, I mean, the numbers are okay. But let me just tell you one thing that you may or may not know, which is called the Newton-Leibniz formula, which is a generalization of the fundamental theorem of calculus. Okay. So what's the fundamental theorem of calculus? It says that if you differentiate, right, with respect to x, an integral, then it's just the integrand, right, plugged in at x. So pretty easy to remember, right? Plug in the upper limit, right? Oh, sorry, f of y dy, right? Well, the tricky thing is, what if the integrand also contains x? Then it's not that tricky, but right, which is exactly what's going on here, right? You see, we differentiate with respect to a, but a appears in the upper limit, but also appears in the integrand. And that's where Newton-Leibniz formula comes in, because you see, right, it provides the formula for this, but if the integral so happens to be independent of x, then you're just back to the, regular FTC. Well, the answer is simple. You combine two cases. The first case is the plug-in case, right? Wherever you see y, you plug in x. And then you move the differentiation inside. Here, it probably is properly referred to as partial, because there's a function of y involved. And this one right here is called Newton-Leibniz formula. Any question? So applying the Newton-Leibniz formula here, what do we get? Well, you see that plug in a here, you get 0, right? So now we move the integral inside. Sorry, the derivative inside, right? But if you differentiate with respect to a here, you get 1 for this thing. So basically it is the integral from 0 to a of lambda e to minus lambda x for the first expression. See, that's the whole point of using the right tool for calculus. It's pretty painless, right? Rather than integrate this and then differentiate back to discover that that's all you get. The second one's the same, right? Plug in a here, but with a minus, because, it's the lower limits, but, you can use your imagination, right? Plug in a here with a minus, but the minus of the integral is still 0, right? And then differentiate, right, with respect to a inside. And what you get is going to be minus the integral from a to infinity of a lambda e to minus lambda x dx. Okay, so far? And that should be 0. And sort of that's what I want to tell you, that using Newton-Leibniz formula is going to be much quicker than. Any question? Now, so that's not the end of the story, right? This is just giving you a nice equation to solve. You still have to solve for this, right? You have to solve for a. But this equation has a lot of meaning. Do you see what that means? Don't forget, right? This is the density of the exponential. So the first one is the probability that the exponential is less than or equal to a. The second one is probability of the exponential is bigger than a, and it's 0, which means that is that equal, which means that is equal to. a half, right? Because they sum up to 1. So do we know what the name of A here is in terms of statistics? It's called a median, right? In contrast to the mean. The median, the value that 50% is below, 50% above, right? The median of the distribution. So, right, then we just have to find A in terms of lambda with that information, right? If you anti-differentiate this, you get 1 minus, right? So e to minus lambda x. Hold on. I apologize. 1 minus e to minus lambda a, right? So e to minus lambda a is a half. Taking log on both sides, right? Remember, log of 1/2 is minus log of 2. You got a is 1/2 log of 2. Well, I mean, this value, sorry, 1 over lambda log of 2. So this value is not super important, but notice that it's nothing like midway, right? There's nothing like midway of a exponential. The exponential has infinite support. But the more valuable message is that, right, the one that minimize the means L1 distance away from a random variable actually is the median, not the mean. The mean will minimize the L2 distance, right? The median minimizes the L1 distance in general. Any question? All right. So this pretty much wraps up the family of random variables I want to talk about for continuous random variables. It's actually pretty small, right? Only 3 random variables. So let me say a few words about the other models that are not discussed. So I'll say a few names here. You might have heard of the T distribution, T with n degrees of freedom. There's the chi-square. With n degrees of freedom. There's a gamma distribution. There's a beta distribution. Gamma, there's some parameter alpha, beta. There's a Cauchy distribution. And then your textbook mentioned the Weibull and the Pareto distribution. Let me see. Yeah, all right. So just a few words. First of all, right? Well, I have a confession to make. I have never used this before in my life, or maybe I have, I just don't remember. So they might be used for something, I don't know. And that's why I skipped them because, these ones are more commonly used in statistics. In fact, if you study math for 81 at Rutgers, you will encounter, right, these random variables. And so they are more for statistical purposes. Not that they are not popular, right? They are probably as popular as the other ones anyway. But within the context of this class, which is probability, which is, I think, leaning more toward modeling, blah, 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 right? I don't think we should drag in these things to, if we have time, we can go back and talk about that. So the T distribution, right, is well known for having a bell shape similar to a normal, but fatter tail, right? So that's sort of like where the T goes in, where you ask, is this a normal distribution or T distribution, or is it a T test or a Z test, right? When it comes to hypothesis testing. A chi-square, if we have 1 degree of freedom, is the square of a standard normal. So it's related to a standard normal. If you have n degrees of freedom, it's the sum of a square of n independent normals, right? Standard normals. The gamma, in some way, is a generalization of the exponential, or sum of exponential random variables. If you sum independent exponentials, you get a gamma with n lambda, I think, depending on how you parameterize this. Beta, I'm not sure if you want to call it a generalization of the uniform, because that sounds weird. But beta basically has finite support, and it kind of allows you to change the density within the support. Okay. So again, these things are in some way generalization of, not the T, right? These two of the gamma, of the exponential and other things we know. And notice that some of them have a lot to do with sum of independent random variables. And we have not talked about sum of independent random variables. And that's sort of also the reason why it's not the place to discuss them yet. Cauchy should be known, if only for the following reason. And by the way, right, let me say this. Even though we skip them, in some way, they can still be on the exam in this way, that all of them have densities. So principle of probability still applies to them, like expectation, variance, right? Blah, 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 probability calculation is as long as the calculus is doable, then it's all fair game. Let's say that, right? They're skipped in the sense that you're not asked to memorize the densities or the expectations, blah, 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 associated with these things. And they're not that likely to be on the exam. But I'm just saying, that doesn't mean that when you see a chi-square, you're like, well, I give up, I don't know anything, right? You can still work with the density, you can still work with expectation. Maybe the calculation is hard, but that's hard on the calculus side, right? Not on the probability side. Now the Cauchy, you should keep in mind for the following reason, that the Cauchy, right, is actually a T distribution with 1 degree of freedom as well. But its density is something like this, I 1 plus x squared. All right, like that. And the pi has to do with the tangent inverse. When you integrate 1 plus x squared, right, you get tangent inverse. The Cauchy has this, let's say, very nice quote property that if you take the expectation of the Cauchy, you're gonna deal with this integral. And you might think that this is 0 because it's an odd function. Actually, the answer does not exist. All right, because it does not converge. You have infinity minus infinity. And so you have seen, right, a random variable with infinite expectation before, I believe, right? We looked at that in this discrete case or continuous case, I forgot. But this is a random variable that, more properly speaking, has no expectation, or expectation doesn't exist, because the integral calculation does not converge, right? So the Cauchy has no moment. The second moment will be infinite, right? But any other moments, right, won't exist. X cubed, yeah, won't converge. Okay. So that's what the Cauchy should be remembered for, as in like a counterexample to certain statements. Like someone says, well, a random variable must have an expectation. And you're like, okay, what about the Cauchy, right? Things like that. Right. Any question? Okay, so let's move on to 5.7. Distribution of a function of a random variable. And we talked about this before, right? In let's say a mild way. So the theme is this: you have x, a random variable, and this could apply to discrete or continuous too, even though here we focus more on the continuous case. So let's say with density, right? Let's say f. You apply a function to it. And here the function in principle can be anything as long as it makes sense. Like you don't take the square root of a negative or you don't divide by 0, right? As long as those things are avoided. And you want to find the density of the all right, that's a thing. And the answer here, right? The answer here also has a thematic, proceeding. You always start with a PDF. Sorry, start with the CDF. All right, because like I said, CDF is probability calculation. PDF is not probability, so they're not conducive to probabilistic calculation, probabilistic principle, like union intersection. So you start with probability y less than equal to y. And then you apply the definition of y, which is phi of x. And here I stop, because to do the next move, I will have to deal with the inverse and how it interacts with the less than equal to. All right, and we can't say much until we see a specific case. Let me give you an example. Suppose you have e to the x is less than equal to y. Then this is equivalent to x less than equal to log y. That's clear. But if you have something like x squared less than equal to y, then this will be equivalent to minus square root y less than equal to x less than equal to square root y. Right? So the treatment is peculiar to whatever function you're looking at. So not much we can say in general, besides the fact that you will have to do with the inverse and how it interacts with less than equal to. But whatever that you end up with, after you do this manipulation, you will end up with probability of x in some region as a function of y, a function of little y. All right. Why do I say in some region and I cannot be more particular? Because of something like this, right? This is not less than equal to, it's not greater than equal to, it's a combination of both. So basically, the whole point is you start with the CDF of y, you move to x in some region. But basically, you have returned y into x because you have density of x. So in principle, you can calculate this out as a function of y, and then you differentiate. And of course, right, actually that's the CDF. All right. So that's a theme. Any question? Now, what do I want to say here? There is something in potentially that can be shortened, which is right from here to here is some calculation, right? Sometimes what you can do is you can skip the last step and just use this, because in the end your goal is this, right? So you can differentiate at this step. But if you differentiate this step, you may end up with the PDF of X and some chain rule. So I'll just make that remark. The last step may be avoided by using the chain rule on the previous step. All right. So let's take a look at an example, right? Let's say X is uniform 0 to 1. And let Y be X to the N. Some integer N. Find the density of Y. So maybe I forgot one thing here, but when you look at little y here, you probably want to do the first step to see what values of little y. In other words, you're looking at the support of the random variable y, big Y. Why should you think of that to begin with? Because it might be relevant down the road when you do the inverse, right? I mean, suppose that this is a negative number for any reason, then you're not going to take the square root of a negative number, right? So anyway, thinking of the support of random variable would be very helpful. So for example, right, if I start out with probability of y less than equal to y here, well, random variable y is x to the n. X is uniform 0 to 1. So what kind of values can big Y take? Also 0 to 1, right? Any number from 0 to 1 raised to n power is still 0 to 1. And so I will proceed as x to the n, and I will. So now the thing, right? See, now it's helpful because I know that y is a positive number. So I just take the nth root on both sides, and x is of course a positive number, right? Positive random variables, right? So basically no absolute value involved. Or maybe I should write as y to 1 over n, because I might have to do some, which is the CDF of x evaluated at 1 over n, y to 1 over n. Okay, so far? Now, if you want, right, we do know what the CDF of the uniform is. So you can plug that in here if you want. But, you know, so what's the CF of a uniform? The CF of a uniform is X, right? Because you integrate one. But let's even skip that step for now, right? Let's show you how to use a chain rule. If you use a chain rule, then you say, right, f sub y of y is d over dy, right? Probably y less than equal to y. So you differentiate this, which is the PDF, right, times the derivative of the inside, which is 1 over n y to the 1 over n minus 1. Well, the PDF of the uniform is 1, so that doesn't show. So the final answer is 1 over n y to the n minus 1 over n, right? Am I right? Hold on. 1 minus, it's n minus 1. 1 minus n, right? Or, yeah, it's just that. So this is if y is between 0 and 1, 0 otherwise. Why? It comes from the support analysis. Any question? Let's say x is standard normal, y equals to x squared. So this is exactly chi-square with 1 degree of freedom. What's the PDF of y? This question may sound scary, but it's not. So first of all, right, what do? We look at the CDF, but for what kind of value of y? Values of y, little y. Well, the normal, right, takes value from minus infinity to infinity. So if you square it, then you'll get values from 0 to infinity. So for y non-negative, right, then this will be probability of x squared that's equal to y, which will be probability of, so because y is non-negative, I can take the square root, right? But now, right, notice that for the standard normal, the PDF, right, is 1 over square root 2 pi e to minus x squared over 2, which, right, is an even function, and I'm pretty sure a lot of you know that is the bell-shaped, right, curve. Which means that basically the probability that is between these two is twice, right, the probability that is from 0 to square root y. Right? And so here we still want to do this CDF version. So let's do 2, right? And then probability x less than or equal to square root y minus a half. A half comes from where? A half comes from the probability x is less than 0, right? Which is the 1/2 of the standard normal, right? Probability less than 0 because of symmetry. Any questions so far? So now to find a PDF, we differentiate. And right, differentiate this gives us 2 the density of x evaluated as square root of y times the derivative of the inside, which is this. And that's it, right? This one differentiate to 0. Which really is, right, 1 over square root of y. And if you plug in square root of y for this function, remembering that y is not negative, you get, so 1 over square root of 2 pi e to the minus y. So that's the PDF of the chi-square with 1 degree of freedom, if you will, done by the, the scheme of the calculation of the distribution of function of random variable. Any question? All right, so that's it, because the rest is just practice, okay? I mean, there's not much I can say beyond this scheme. The rest are just like, you just keep doing it until, you master the technique. Okay, so let's move on to chapter 6. Jointly distributed random variables, or joint distribution. So 6.1, let's just say that the title is joint distribution function. All right, so let's just have a general discussion now first. So far, right, what we've been focusing on is the behavior of one single random variable. All right. We haven't looked at, let's say, 2 random variables together or n random variables together. What's an example, right? Well, you might think of something like, let's say, toss a pair of dice, right? And so in this way, you have x as a value of the first dice and y as a value of a second dice. So basically, the value here is going to be a 2-dimensional vector, right? With, let's say, 1 for the x and 1 for the y, let's say. Now, when we say this, it's still sort of pretty simple in the sense that intuitively the pair of the dice are independent. So whatever statement you want to make, for example, right? Because x, y are independent. In fact, I mean, we didn't. So actually, let me draw back. we have not defined what it means for two random variables to be independent here yet. Okay. What I should say is that these events are independent for any I and j. The events at x equals to I, y equals to j for the Fairdice. So that's what it means really for xy to be independent. But anyway, right? The point is this, that basically this function right here is what we mean when we say, I mean, for the discrete case at least, that we look at the joint behavior of x and y together. And the interesting thing comes when we can't separate this out as a product, meaning that x and y have some correlation, or x and y have some dependency with each other, right? So basically, for example, we have a pair of x and y as random variable. We want to be able to say that this as a function of I and j. That's it, right? So we want to ask, so this is for the discrete case at least. So again, right, this is called the joint distribution or the joint probability of x and y. So several questions, for example, right? What properties does Fij have? Can we recover? So now this is called the marginal distribution from the joint. So this is called the marginals. All right. So basically, right, from the joint behavior, can I rediscover the individual behavior? Or you could ask even conversely. Can I reconstruct the joint from the marginal? Sorry. Something like, so let me tell you, right? The answer here is yes, the answer is no. Okay. But other things like, anything like expectation going on here, but you have two random variables. So what do we mean? Something like variance. Actually, the thing is more like a covariance, right? What's the covariance between the two random variables? What else? Conditional distribution, which we kind of touched on, right? In that question. Conditional probability, right? So all of this, right, will be encoded or will be sort of like given if you know the joint distribution of the two random variables. So basically, joint distribution in one word is the interaction, all right, between the two random variables. So that's the discussion. Of course, I've been doing this under the discrete random variable just to make things easy, but it will have the discrete case and the continuous case, okay? So let me see here. Let's start with the definition here. For any two random variables, x and y, the joint CDF, okay, the joint cumulative distribution function of x and y is defined as big F you can do xy here just to have the notation. Let's say at little x and little y will be probably x less than equal to x, y less than equal to y. All right. So again, right, it's very similar to what I was saying above, but this is like the mass function. And here, right, we're defining it generally. So we're doing it with the CDF. But notice it's joint, right? Because it's the event and this and that. Okay. So I don't know. Maybe something like this is obvious, but proposition. Probability, let's say A1 less than X less than A2, B1 less than Y less than equal to B2 is F A2 B2 plus F A1 B1 minus F A1 B2 minus F A2 B1. Do we see why? Do we even know what's going on? Why is this true? This is true for any value A1, A2, B1, B2. So the reason, right, is the following. And when you have like joint distribution, especially with two random variables, it's helpful to draw a graph to demonstrate, right? The first thing you should notice is that they're referring to a rectangle. A1, A2 for the X, B1, B2 for the Y, right? Now, again, it doesn't mean that you have to be continuously inside a rectangle. It can be discrete values, right? But anyway, the region is the region enclosed by the rectangle. Okay. Now, what's f of a point? F is this probability, right? Meaning that, say, at a point, what are we looking at? Below the value and to the left of the value. Sorry, below the y value and to the left of the x value. So we're looking at the, so if you extend that, right? We're looking at all the areas here, if it has any mass. Okay, for a point. So if you will, it's really the area language. What's the area of the rectangle? Area in terms of relative area to the weight, right? If you want to look at this rectangle, right, area of the rectangle, you should look at this big area, subtracting the small area. Hold on. Not really, right? You add, but why? Let's see. So you take this area, right? You subtract A1, B2, which is what? You subtract this part, which makes sense. But then you subtract this, right? Which is, sorry. So again, right, you do this, you subtract away this, and then you subtract away this. But you see, you do a double subtraction. So that's the inclusion exclusion, right? So you have to add back. So it's literally the inclusion exclusion formula. That's all there is. But you know, with the two-dimensional taste of a rectangle. Any question? So now that's the joint CDF, and the joint CDF, this definition makes sense, or really is a universal identifying feature for any kind of random variable. And by kind here, we have in mind discrete or continuous random variables. As I said before, right, discrete or continuous random variables, CDF makes sense for all of them, even mixed. And it's really the unifying feature to define them, to defining them. But if you specialize to both discrete right? And we know what this means. That means that the support of both X and Y are on discrete values. And you see, right, if that's the case, then if you draw them together as on the Cartesian coordinates, then together they form dots, right, on the plane. Yes. So then you will look at probably X equals to I, Y equals to J, and this is called the joint mass distribution function, mass function, joint probability mass function. Okay. So let's see if we understand. Suppose that you're given this function somehow, meaning that it's given for any ij, right? How can we find the CDF based on the joint mass function? I mean, maybe I'll replace this with A and B. Makes it any easier. So in this chapter, right, in chapter 6, you have to start thinking calculus 3, right? You have to start thinking multi-integral context. So you want to find this region, right? Well, all you do is you integrate over all the areas, right? Which means you sum, is a double sum of this, where you sum all over all values of I less than equal to A, and you sum over all values of J less than. Okay. Now, same thing, given this, find probability X equals to I. And again, right, this is called the marginal of X. A marginal, yeah. You know, the word marginal only sort of comes up when you have the joint. The reason, right, is if you look at, like, let's say table 6.1 in your textbook, it'll have something like this. It'll have, let's say 0, 1, 2, 3 for the values of I. I'll have 0, 1, 2, 3 for the value of J. And if you're in something like this, 10 over 220, 40 over 220, 30 over 220, 4 over 220, and then, you know, 30 over 220, 60 over 220, 18 over 220, 0, so on and so forth, right? Basically, each of this entry is a probability, right? That x equal to this value and y equals to this value, so on and so forth, right? But and the distribution, right, of x and y are calculated over here. So this is the distribution for x. The entries for x is over here, and the entries for y is down here. And that's why it's called a margin, right? You have the paper and you calculate this on the margin. That's why it's called a marginal. But anyway, so given the joint like this, how do we find the probably x equals to some value? Sorry, I think I mistake things, right? These here are the i's, and this is other j. Because this is row 0, row 1, row 2. X is the horizontal coordinate. This is column 1, 0, column 1, column 2. Right, these are the vertical coordinates, so that's the j. Well, you see, right, from the margin, sorry, from the joint, the margin can be calculated by summing over all possible values of y. Why so? Why is this is just the law of total probability, right? Remember, the law of total probability says probability of any event is a sum over probability f sub I equals 1 to n, if f sub I forms a partition of the sample space. What's a partition of a sample space? It means events that are mutually exclusive, whose union, right, is the whole sample space. Well, guess what? Y equals to j are mutually exclusive because y cannot take both values at the same time. But if you go over all possible values of y, well, you have worked over through everything possible, which is a sample space, right? So basically, long story short, you sum out the y part, you get the x part, right? It's similar to the double integral where you integrate out, right, one coordinate and you get the other coordinate left. So in terms of the table, for example, right, you would sum the row sum, you will get the marginal of x. For example, right here, probability x equal to 0 will be 84 over 220. This will be 108. Something like that. And if you sum over columns, you will get probability y equal to 0, probability y equals to 1, etc. So in other words, probability of y equals to j will be a sum over all values of I, like that. Any question? Oh, let me see. So we have 5 minutes, right? I wonder what quiz are we on. Quiz 4.
Yeah.
Thank you. So let's start with the one question, right? 6.1. A, right? So this two fair dice are rolled. Find the joint mass function, prop mass function of x is the largest value on any die, and y is the sum of the values. Let's just look at this question and we'll continue next time. So the best way to answer this, right, is through a table. Where you list out all values and you write down the probability that x takes on that value and y take on that value. So for example, right, what values can x take? I think basically anything, right, from 1 to 6. What values can y take? 2 to what? 12, right? So for example, what's the probability that the max value is 1 and the sum is 2? One over 36, right? Because that the only chance is 1 and 1, right? What's the probability that the max value is 2 and the sum is 2?
Two over 36.
No.
Oh, 0.
0, no? Because the max value is 2, it means one of them is 2. How can the sum be 2, right? So 0, and then the rest is? Right. What's the probability the max value is 1 and the sum is 3?
0.
Yeah. You see, the thinking is slightly complex, but same thing, right? Because the max value is 1, that means 1 and 1. How can they sum up to 3? Max value is 2 and the sum is 3. Two over 36, right? 2, 1, 1, 2. Right. Max value is 3, sum is 3. 0. And so on, right? Maybe let's do a last row. Max value is 1 and sum is 12. No way. No way. No way. No way. No way. Agree? So one last thing. If you sum up all the entries in a joint probability table, meaning sum over all I and sum over all J of this, what should you get?
1.
Correct. Right? So that's it, right? The total mass is 1. But instead of being on a line, now it's on a plane. Okay? So, all right, let's stop here today. We'll continue next time.
Thank you.
Thank you.